Yes, let's continue with our lecture. Yes, any questions? Yes.
Bu çizdiğiniz spektrumdaki o shiftlerde herhangi bir peakler arasındaki peakler herhangi bir nokta arasındaki değişiklik oluyor mu shift ettiğinde?
What do you mean?
Grafik shift ettiğinde hiçbir şekilde hiçbir değişiklik.
The graphic is not shifting. The peak is shifting. The shape is changing. Well, you see, they all start from 0. They don't go to negative frequencies. So they go up very fast at low temperature. At higher temperatures, they go slowly, they increase slower. There's shape different change. Other questions? Yes? Well, you see, what does it mean to appear larger? Just do an experiment, an assignment for you. When you see a huge moon on the surface of Earth, okay, just take some pen or pencil, measure its angle. What is the angle it's spread? When the moon is very small at the top, yeah, I mean, it appears larger, but it's not larger. Now, if you go straight towards the moon, will it appear larger? Yes, the angle it extends will be larger because the distance will be shorter. Its radius will be the same. The radius of the disk you see will be the same. But still, it will be a disk of the same size, whether it is close to you or further away from you. The shape is exactly the same, but it extends a larger angle. Does it mean it appears larger if it's closer? If your answer is yes, yes, it appears larger. Back to black body. Any questions on up to this point? You see, on one hand, we have observations. This is what we observe. Then there is the Planck, who proposed that, well, the spectrum should be given by this expression over there. So what are and if you would plot it, it actually works quite well. And furthermore, let's look at some properties of this shape, of this function. du is 8 pi h nu cubed divided by e to the power h nu over kt minus 1 d nu. Well, let me just rewrite it. This is 8 pi h nu over kt cubed times kt cubed over h squared 1 over e to the power h nu over kt minus 1. Why did I do this? Well, nu appears here. I just rewrote the nu, the prefactor nu, in a combination of the same combination. That's what I did. So that I can write this d nu in terms of, in fact, a single parameter, h nu over kt. So du is equal to h pi k cubed over h squared t cubed x cubed divided by e to the power x minus 1. Okay, you see, the only frequency dependence is over here. When you are plotting this as a function of the frequency, you are actually plotting it as a function of x. And that function, sorry, that's x cubed. No, it's d nu. It's still d nu. Well, you see d nu over there, d nu over here. I didn't convert it to dx. Well, this function, if you would plot it, as a function of x. This is x cubed divided by e to the power x minus 1. It has such a shape. For very small values of x, this e to the power x minus 1 behaves like x. So x cubed divided by x, so it goes as x squared. For large values of x, well, this is huge, so ignore the 1. So it's just x cubed times e to the power minus x. Although x cubed is increasing, e to the power minus x will just send it to 0. So this will be its shape. It has a maximum at some value of x0. And at that value, it has some maximum number, whatever the number is. I don't really care about x0 and that maximum number for the time being. Now, if you go back over here, what is the peak value? Well, you see the peak value of this function is independent of temperature. It only depends on x. It is just a number that this function doesn't have any parameters appearing over there. So it's just a number, the peak value. Well, if you look at over here, the peak value is proportional to T cubed. If you increase the temperature, you see if you go back over here, these plots are not strictly correct. As you increase temperature, the peak also should go up higher and higher as the cubed of the temperature. What else can we say? Well, the maximum appears at x0, which is h nu 0 over kt. The maximum frequency is k x0 over h times t. So you see, the position of the frequency at which that spectrum makes a peak, it shifts linearly with the temperature. If you double the temperature, the frequency will be doubled. This temperature over here is the Kelvin temperature, by the way, not the Celsius. Or you can go to write the energy as a function of wavelength rather than the frequency. How are the frequency and wavelength related to each other? C over lambda. So this was 8 pi nu squared h nu divided by e to the power h nu over kt minus 1 d nu. If you go to lambda, this becomes 8 pi h c over lambda cubed 1 over e to the power h c over kt lambda minus 1 times c d lambda over lambda squared. I ignore the 1. I ignore the minus 1, sorry. You see, d nu is minus c over lambda squared d lambda. Well, that minus sign, the only thing that minus sign tells me is that if you are increasing nu, if d nu is positive, that means d lambda should be negative. You are reducing the frequency. That I'm not interested in, so that's why I ignore the minus sign here. Well, let me just rewrite this slightly, as in the case before. It's 8 pi h c over lambda to the 5th power. Let me also add the h and kt. Again, I just created this combination over here. 1 over e to the power hc over kt times lambda minus 1 d lambda. Well, let me correct for the coefficients. So here I have just 1h, so this divided by h to the 5. Kt to the 5th power, and here I have c to the 5, so there's another c over there. Well, now I can define this ratio as, let's say, y. Well, in fact, that ratio is exactly x, the same x as before. But still, let me call that y. So this is 8. Let me ignore the coefficients. T to the 5, y to the 5th power divided by e to the power y minus 1 d lambda. So this basically tells me that if you would plot du by d lambda as a function of lambda, at a given temperature, let me just plot the other one. Y to the 5th power divided by e to the power y minus 1. Well, this starts like y to the 4, increases for large values of y due to the exponential in the numerator, it just goes to 0. And it has a maximum value here at y0. By the way, y0 is not equal to x0, because here I have a different function. When the function where x0 is the other function had x cubed, this is y to the 5th power. So again, you can find the wavelength. So hc over kt lambda is equal to y0. Let's call this y0. Y0 is the wavelength at which the energy density per wavelength is a maximum. And this gives you t times lambda 0 is just some constant. This is called Wien's displacement law. So t times the wavelength at which the majority of the radiation is emitted, their product is always constant. If you increase the temperature, the wavelength decreases. Just note, lambda 0 is not equal to c over nu 0. Okay, so up to here, this was observation. And Planck successfully came up with a function that explained all the observations. Again, this Wien's displacement law was discovered before Planck's formula. And that constant was measured, and then Planck predicted that constant using his expression. Of course, the problem is, now the question is, what is this factor? How can we interpret this thing? Well, actually, if you write this, this is just h nu. Well, let's forget this h nu for the time being. E to the power minus h nu over kt. And from 0 to infinity. Okay, for the time being, well, if you just sum from n is equal to 0 to infinity, this is what you will get. Okay, this sum probably doesn't mean much to you for the time being. Again, remember this formula 2 years from now. No. It is a Taylor series. Well, this formula basically tells me that energies can exist, or let me put it this way. Allowed energies Okay, let's summarize what has been going on. On one hand, we have this cavity, which we are using to model our black body. The cavity is not the black body, but the hole in the cavity is our black body. So we are trying to understand what is the radiation, the properties of the radiation inside. Well, where does this radiation come from? Well, the cavity is made up of some material, some atoms, which are made up of charged objects. So inside the walls, there are charged objects which are vibrating due to the temperature. But since they are vibrating, they are constantly emitting radiation and reabsorbing them. Some of that radiation is inside the cavity. So these vibrations, if you just think of one of the atoms, let's say in the wall, it is vibrating. While it's vibrating, it's emitting some radiation at various frequencies, at different frequencies nu. And then then that radiation just travels through the cavity and hits the other wall where there are other oscillators. And this radiation hits the wall, it's absorbed, some of it is absorbed by that oscillator, and that oscillator emits some other radiation. So there's this constant emission and absorption of radiation by the oscillators. Now, what this formula told Planck was that those oscillators cannot really give any energy, but can only give, if it is oscillating at a frequency nu, it can only give energy as a multiple of h nu. You see, if you just imagine collisions, if two objects collide, they can just transfer energy. If let's say that you have these two spherical balls, if they hit head-on, they will probably transfer a large amount of energy. If they just barely touch each other, they will just transfer a very small amount of energy. They can transfer any amount of energy that they like. Well, not they like, but any amount of energy depending on how they collide. And the amount of energy they can transfer can take continuous values. But what this told Planck, this expression told Planck, was that when this electromagnetic radiation and the oscillators in the walls, when they are exchanging energy, they can only, the oscillators can only emit energy at a given frequency nu in terms of multiples of h nu. This is what is called the quanta. Quanta is just, you can just think of quanta as a package. So these oscillators can only emit energy in terms of packages. Well, still, if you look at a single oscillator, it might be oscillating at different frequencies. There is no restriction on nu. Nu can take any value, just like in these plots. In this plot, nu can take any value, but if you just pick one nu, at that frequency, every oscillator can only emit a multiple of h nu. It cannot emit 0.5 h nu energy. It can only emit an integer multiple of h nu. Why does it do that? We don't know. It's just like asking, why is f is equal to m times a? We don't know. It's observation. It's what nature tells us, that if you are restricted yourself in Newton's in phenomena that can be explained by Newton's dynamics, the force should be equal to mass times acceleration. Why? It just behaves like that. Similarly here, why do these oscillators emit only in multiples of h nu? We don't know. It's just how nature behaves. Well, we hope to understand it one day, but we are not yet there. Well, we will have an explanation for why multiples of h nu towards the end of the course, but I don't call that an explanation because we will be explaining one unknown in terms of some other thing which we do not know why. Okay, so this is our first, if you think of it historically, this is kind of our first observation. Up to that point, okay, the electromagnetic radiation was continuous. The oscillations, they can oscillate at every frequency, and you can give an arbitrary amount of energy to every oscillator, including the oscillators on the wall. But it turns out not to be correct. So at least if we want to understand the blackbody radiation, we have to assume that the oscillators on the wall can only give discrete amounts of energy to the electromagnetic radiation in the cavity. Now, let's, well, before finishing the discussion of the black body, let's calculate a couple of more properties of the black body. So this is the energy per frequency emitted by the black, not emitted by the black body, but this is the energy density per frequency inside the cavity. What is the total energy density inside the cavity? Well, if you want to calculate the total energy density, just integrate this over all frequencies.
Başta yapılan şeyde belirli bir kübik bir şeyin içindeki enerjiden ufak bir yerdeki enerjiden yola çıkıp total'a gitmek değil mi?
Well, you see, in the beginning, what we said what this was the energy per volume in the frequency range d nu. Still, we are looking at energy per volume.
Değişen neydi burada? Yani şey olarak söylüyorum. Physically expression'ın yanlış olan kısmının düzeltmesi nasıl bir şekilde geldi buraya?
He introduced this function.
Bir tek onu koydu.
Yeah, that's the only thing he did. He just, looking at the observation, as your friend pointed out, he just fitted our function. One of you had guessed that it should be normal distribution. He probably also tried the normal distribution, but it didn't fit well. So he came up with this function, which fitted perfectly.
Ama hala bir volümün içindeki
Yeah, we are still looking at the cavity. Now we will go to the black body eventually. Well, first let's calculate the total energy. The total energy density, which is 8 pi h nu cubed divided by e to the power h nu over kt minus 1 d nu over all energies. Well, let me just make a change of variable now. H nu over kt, or d nu is equal to kt over h dx. So this just becomes 8 pi h kt over h to the fourth power from 0 to infinity x cubed dx e to the power x minus 1. Well, it's 8 pi h. These are all constant. This is Boltzmann constant. This is Planck's constant. This is just a number. Just put it, you can calculate it numerically. This is just, that you can also calculate in terms of pi's. I don't remember the expression now. But this is just some constant multiplied by t to the 4. So the energy density inside such a cavity is, let me just call it A times t to the 4. This is the total energy density. Well, this is our cavity. The energy density is A times t to the power 4. And this energy is just moving in every direction. Some of them is flowing in that direction, some of it moving upward, some of it moving in that direction, etc. Some of them will go through this area. The total amount of energy flux through this area will also be proportional to this area. The larger the area, the more there will be the leakage. So we can define the total power per area. This is the power emitted by the black body per area. Well, it will be proportional to t to the 4. The larger the t, the larger the energy density, the larger the power will be. The power, you can think of it as, here you have some kind of a density which is moving at the speed c. The flux of what then, the flow corresponding to a density is nothing but the density times its speed. Because if you had charges moving, the current you would just define as the charge density multiplied by the speed of the charges. So here we have some energy density flowing with the speed c. Of course, it's not flowing only in one direction, it's just flowing in every direction. So there is a geometrical factor c over 4. So this is equal to, this is defined as sigma times t to the 4. This is the Stefan-Boltzmann law. And keep in mind that you see u, this a over here is a function of the Planck's constant, Boltzmann constant, and that's numerical value over there. Well, basically, sigma is just expressed in terms of h and k, and that's it. This was measured experimentally, and now we have a theoretical explanation of it. And they match.
So this total expression is the sigma?
Yeah, all of them. You have the 8 pi h's, k's over there, and then you have the c over 4 factor over there, and that gives me the sigma.
How did we drag C over 4? 4 comes from geometry, but I don't understand what it is.
It's a definition. Well, in U, I have this constant A. Now I have that constant C and 4. I write all of that as a new constant sigma. Well, the important thing is don't try to memorize all these C's and factors, 4, etc. But the idea is that the power emitted by the black body should be a function of t to the 4. It should be proportional to t to the 4. And the proportionality constant, which is called the Stefan-Boltzmann constant, can be expressed in terms of all the other, like the Planck constant and the Boltzmann constant. So that's the main idea. That's essentially the success of this Planck's explanation. Are you following the discoveries of exoplanets? No? You are not interested in space? Aliens living in space? When you now, I do advise you to follow the recent discoveries in various branches of science. But if you read some popular articles on the discovery of the planets, they get excited, especially if they are in their distance from their sun is at a particular distance. And that distance is essentially the distance in which liquid water can exist. How can you calculate that distance? Now, essentially, you know everything that you need to calculate that distance.
You can find energy radiated by the star using that temperature. And we can find temperature by using color.
Well, you see, if you look at a star, if you look at the spectrum, if it will be quite accurately described by the black body. You can look at its spectrum, and if you can determine where the peak is, well, the position of the peak, if you calculate the spectrum as a function of frequency, the position of the peak tells you what is the temperature of the star is. So you can measure the temperature of stars. And once you know the temperature of the star, well, you should also determine its size. If you know the size of the star also, well, the surface of the star is almost a black body. So you know how much energy it emits per area. So by looking at the star's surface area, multiplying it with sigma times the temperature of the star that you have determined, you can determine how much energy it emits as an electromagnetic radiation. Well, let's see that some of that electromagnetic radiation will travel and hit the planet. The planet you can model as a black body itself also. So if it's a black body, it will absorb all of the energy. Well, if you want, you can just cheat from Earth, and the Earth absorbs, I think, 50-60% of all the radiation falling onto it. So it will absorb that much radiation from the star. But if it is also at a temperature Tp, at the same time it will be emitting black body radiation. When the system is in equilibrium, the amount of radiation it absorbs should be equal to the amount of radiation it emits. Of course, the temperature will not be uniform. The side where the star will be somewhat hotter than the side away, facing away from the star. But you can define as some kind of an average temperature. So assume everywhere is of the same temperature. So you know how much it emits. You know how much it absorbs. You know the temperature of the star. By knowing this distance, you can determine what is the energy flux falling on the planet. You can determine how much energy it absorbs. You know the cross-sectional area. So that is how much it absorbs. It emits proportional to its temperature to the 4. And these two should be proportional to each other, with proportionality constants written in terms of the distances between the planet and the sun, the surface area, the radius of the planet, etc. So that way you can determine what should be the temperature of the planet. Well, if you try that for Earth, the temperature of the Earth just turns out to be 7 degrees Celsius, which is not bad. It should be around that value. I don't really know the average temperature of Earth. But if you look at Ankara, for example, nowadays the average temperature is kind of around 5 degrees. Well, in winter it goes down to -2, -3 degrees. In summer, something like 40 degrees. Well, if you look at the average, not bad. Not far from 7 degrees. I don't know. Well, as your friend points out, one of the problems is that we only see huge planets. And, well, smaller planets are harder to detect because we basically measure the wobble of the star as the planet is orbiting around it. Smaller planets. Yes, that was the word, the habitable zone, yes. Well, this will be a very crude prediction, let's say, or very crude calculation, but it works fine. You see, not all the radiation of the sun is also in the form of electromagnetic spectrum. The sun also sends all kinds of other particles, which this basically ignores. Plus, not all the source of the heat of the Earth is from the sun. You see, the Earth, I mean, even if one day Earth just goes away from the Earth, from the sun, its temperature doesn't go very low, because some of the heat is actually created by the nuclear reactions in the center of the sun. So it will remain hot for quite a long time, even without the sun. It still will get cold, but not very cold.
Is it because the only way of dissipating heat is radiating?
For Earth, that's the only way. Other questions? Well, not really. You see, the amount of heat it absorbs is proportional to its radius squared, because its cross-section is proportional to its radius squared. The amount of heat emitted is also proportional to the radius squared, because it's the total surface area. When you equate the two sides, the amount absorbed to the amount emitted, the radius just drops out. You don't need to know the radius of the planet. It only depends on the temperature of the star and the distance from the star, not on the size of the planet. So, okay, what we had achieved up to now, for some reason, it turns out that the matter, when it's emitting radiation, it can only emit radiation in packets of h nu. So, in fact, that is why we have this dip, not the dip, but why for large frequencies the energy, the spectrum just goes to zero. You see, if the oscillators could emit frequency at any value, they could just emit large frequency radiation, but having very small energy. So they would accumulate. And since they accumulate, they cause this ultraviolet cutoff. But what happens over here is that now they cannot emit radiation of frequency nu with arbitrarily small energy. They have to emit them either all at once or none at all. But they don't have that much energy. The oscillators have a very finite energy. So they cannot emit very high energetic electromagnetic radiation. That is why there are not many of them in the spectrum. Their energy increases, the energy of the oscillations increases. Well, the oscillators themselves, they satisfy this equipartition theorem quite precisely. So since the atoms making the walls satisfy the equipartition theorem, their energy increases linearly with temperature. If you increase the temperature, their energy increases, so they can emit more packages. They can emit packages of higher energy because now they have the necessary energy. They can just emit them all at once. So that's why the peak at larger temperatures, the peak just moves at larger frequencies. But they cannot emit arbitrary large frequency packages because they don't have that much energy. They can only emit the energy they have. So this idea that the energy is emitted by the packages, by packages of h nu, it explains the observed spectrum. Now, on Thursday, we will start studying the photoelectric effect, which will tell us that actually light itself is made up of packages independent of the oscillators.
Sorry for my ignorance, but is this the reason why the stars light when it turns like yellow, white, blue?
You mean the flickering?
No, the colors of stars.
The colors of stars depends on the temperature. Well, is there a narrow color range? Let me see. Well, what I'm thinking about is, does there really exist a narrow color range, or are we aware of the stars only in the visible spectrum?
I was going to ask something about that actually, because I was wondering if the UV light coming from our sun is as a result of the absurdly high temperatures in its core. Since the core is somewhere around billion degrees, maybe the radiation is somewhere around ultraviolet range.
You see, let's go. The spectrum of all the stars more or less looks like this. And the visible color will depend on its temperature. If it is at the lower end, well, we have the red stars. If it is at the higher end, then we have the white stars. If it will be even higher, so we will have like this, they will become blue. But at the same time, they will be shifted. The further away stars will be red shifted to lower frequencies. So I would expect most of the stars we see will be more red than other colors. If they are very far away, they will be so much red shifted that we cannot see them by our naked eye. So they will be mainly emitted at the infrared. Well, if you correct for the colors, well, since the mechanism of heating the star is more or less the same for every star, I still think the spectrum will be more or less the same. You see, most of the stars are heated by fusion of helium, hydrogen. So its temperature should be more or less the same. But I'm just guessing. It's not something that I can definitely say. Okay, so see you on Thursday.